Hey, this is Miss Gray. Welcome back for some more AP Chemistry. This is podcast 12.2, and I broke it into two parts. This part is about the differentiated rate law. So let's write a rate law. The first example has ammonium and nitrate reacting to form nitrogen gas and water. So we're going to write the rate law for this reaction where there are three experiments to determine the rate. In the first experiment, we started with 0.1 molar concentration of ammonium and 0.005 molar nitrate. But in the second experiment, the concentration of nitrate was doubled. So what you see here is that when the nitrate concentration is doubled, the rate also doubles. So what that tells us is that this reaction is first order with respect to nitrate, because when the concentration of nitrate was doubled, the rate also was doubled. Now let's look at what happens with ammonium. In the experiment 3, the ammonium concentration was doubled compared to experiment 2, but the concentration of nitrate was held constant. So let's compare the rate for experiment 2 and experiment 3. As you see, the rate went from 2.7 times 10 to the minus 7 to 5.4 times 10 to the minus 7. So when the concentration of the ammonium was doubled, then the rate also got doubled. So this is a rate that is also first order with respect to the ammonium. So to write the rate law, we simply write that the rate for this reaction is equal to K, or some constant K, times the concentration of ammonium to the first power, which we don't have to write a 1, but we can. It's not wrong, it just looks funny, times the concentration of nitrate, also raised to the first power because it was first order with respect to both of these substances. So how do we solve for K then? Well, we're just going to put some values into this equation, and we might as well start with experiment 1, right? So let's take experiment 1 and plug in the rate was 1.35 times 10 to the minus 7 moles per second, or molar per second, and that's equal to K times the concentration of ammonium, so 0.1 molar, times the concentration of nitrate, 0.005 molar, and we're going to solve for K. So we'll divide both sides by the concentration of ammonium times the concentration of nitrate, and that was in moles per liter. Let me get that unit in there so you can see what happens to the units of K. So that's canceling away. K is then equal to, let's get our calculator out. Oops. Okay, here's my calculator. All right, so we're going to take 1.35 times 10 to the negative 7 divided by the product of 0.1 times 0.005. All right, we end up with K equals 2.7 times 10 to the minus 4, and let's check our units. The moles per liter cancels only one time, so I end up with units for K that are equal to 1 over molarity times 1 over second. That's pretty typical for a second order reaction. So now we've written the rate law, that's this one. And we solved for the value of K. Now the best way to solve for K is to do this for each experiment and then take the average. So I just put in experiment 1 into my rate law. The best way is to also test this for experiment 2 and experiment 3, and then take the average value so that you get a more accurate value for K, for the rate law constant. You should all, by now, be familiar with this idea that K stands for constant, because constant starts with K. Constant, only one. But this one's different from the equilibrium K. In equilibrium, the K is capital, and in rate laws, it's lowercase. So let's talk about orders of reaction. I referred earlier to the reaction being first order. So the differential rate law, or just the rate law, is simply where we write the rate is equal to some constant times the concentration of one substance raised to some power times the concentration of some other substance raised to some power. And we have to use experimental data to figure out what those powers are. So the rate constant, K, is not something that we can calculate from stoichiometry. We have to do experiments to figure it out. So if we have a rate where the rate law is equal to the constant times just one thing, or A raised to the first power, we call that a first order rate law. But if it's raised to the second power, then we call that a second order rate law. That would be a situation where doubling the concentration of A results in the rate being quadrupled, right? 2 squared. Now, what if we had the concentration of A times the concentration of B? That would be like A is raised to the first power, B is raised to the first hour. So overall, we have two things. We add up these exponents for an overall second order rate law. It would be the same as having A raised to the first power. Now, if we have A to the first and B to the second, then that would be overall a third order rate law. And in this situation, that would mean theoretically that 3 particles have to collide in order for this reaction to take place. And that's going to be a rare circumstance where 3 things collide. You have to get this from experimental data, though. You can't find this from the stoichiometry of the balanced equation. So let's clear out this writing. The units for K then depend on the order of the rate law. So if the units for rate are molarity per second, or moles per liter per second, then the units for K will have to be whatever units work out to make the rate law equal to molarity per second. Let's go back to that. So in a case where we have rate is equal to K times A, concentration of A. This is a first order rate law, right? Where these units are moles per liter per second, and the concentration of A is going to be moles per liter, then the units for K are going to have to be, let's divide by moles per liter on both sides. And then that cancels, whoops, the M, not the S. My pen got a little carried away. So I'm left with just 1 over second because the moles per liter canceled away. So the rates for K in a first order reaction is 1 over second. What about a second order reaction? In a second order reaction, we would have rate equal to K times A squared. So let's put units in. Rate is in moles per liter per second. K is what we're trying to figure out. And then A squared would be molarity squared. Moles per liter per second, or just moles per liter squared. So I'm going to divide both sides by M squared. So this will allow me to cancel away just one of those. That leaves me with per second and per mole, and that's it. So 1 over seconds and 1 over moles, and that's the units for K in a second order rate law. We could do the same for third order. In equilibrium, that capital K has no units. But in kinetics, K has units that have meaning. They are important. So units are meaningful and must accompany the numbers. No naked numbers are allowed in kinetics. So here's another example of how to use the differentiated rate law. In this reaction, S2O8 ions react with iodide ions to form the sulfate ion and the I3-. So we have 4 tasks. So let's get started on this one. Part A says determine the rate law of the reaction. So I'm going to get us some room to work, and I'll show you how we set this up. So we start by writing just a generic rate law. Our rate is going to be equal to some constant K times the thiosulfate ion. I think that's the name of that ion. I don't know. Raised to some power that I'm going to call X for now until I figure out what number goes there. Times the concentration of the iodide ion. Raised to some power that I don't know yet, so we're going to call that Y. Our job now is to figure out the value of X and the value of Y. So I'm going to use the data from my experiments. In fact, I'm going to compare experiment 2 to experiment 3. No, experiment 1. And the reason I'm going to choose those two is that the iodide remains constant while the thiosulfate is going to change. And so that's going to allow me to cancel away one of them, and then I can figure out the other. And I put the one with the larger number on top so that I don't end up with fractions. I like to do the kind of math that's easy. So I'm going to put the rate for experiment 2 above the rate for experiment 1. So I'm getting this directly from my data table. And then I put in K for experiment 2 and K for experiment 1. All right, now let's put in the concentration of thiosulfate in for experiment 2. That concentration was 0.027 molar, and that's going to be raised to some power that we're calling X. And in experiment 1, that same concentration for the same substance was 0.018 molar. And that's also raised to the X power. Now let's do the same for the iodide concentration. Read from your data table. In experiment 2, the iodide concentration was 0.036, and that's raised to the Y power. And in experiment 1, the concentration of iodide was also 0.036. That's why I picked those two experiments, so that I can just say those are the same. One thing divided by itself is equal to 1, so those just cancel away. Also, the K, since K is constant, cancels away. One thing divided by itself just gets to go bye-bye. So now use your handy calculator. Okay, so let's do this math. 3.9 times 10 to the negative 6 divided by 2.6 times 10 to the negative 6. And that gives me 1.5. So 1.5 is equal to 0.027 over 0.018. And those are raised to the power of X. So I can say that's the same as dividing these two numbers and raising that quotient to the power of X. So let's see, what is that quotient? 0.027 divided by 0.018. Hey, that's better, it's 1.5. And this is going to make my math easy. Usually you're going to end up with numbers that work. So this tells us 1.5 is equal to 1.5 to the X power. So what is the value of X? In this case, the one thing's equal to itself. What does that mean? It's x is equal to 1, because 1.5 to the first power is just 1.5. So we know that this reaction is first order with respect to thiosulfate. Now let's see what happens with iodide. So to figure out iodide, the experiments that I chose to use here is experiment 4 divided by experiment 2, because in that case my iodide concentration was changing, and that's the best I can do. There's not one where thiosulfate is held constant, but now that I know what its exponent is, we can handle that. Let me show you how. I put experiment 4 over experiment 2 because experiment 4 has a higher number, 1.4 times 10 to the negative 5, and higher than experiment 2, 3.9 times 10 to the minus 6. This allows me to have like a whole number that's not some fraction. I don't like fractions. And then we write the rate law for experiment 4, K times 0.050. There's my thiosulfate raised to the x. Wait, I know what x is now. X is 1. So let's just put a 1 in there. So 0.05 is raised to the first power, but I don't know yet the concentration or the exponent for y. So I just put in the concentration of iodide raised to the y power. Now let's write the rate law for experiment 2. So we know constant K is there, and thiosulfate is raised to the first power, and then iodide is raised to the y power because we don't know what that number is yet. Now we need our calculator to take care of the math. So what did we have? 1.4 times 10 to the negative 5 divided by 3.9 times 10 to the negative 6 is equal to 3.589, oh, blah, blah, blah. We'll keep that in the calculator, but I'm just going to write here 3.58. And that's equal to, cancel out K. Let's do this math, 0.05 divided by 0.027. 1.85-ish. So we'll, of course, keep the values in our calculator and don't worry about the rest. And that's multiplying 0.072 over 0.036. And that's all raised to the power of y. We're trying to figure out what is y. So my first thing to do is to divide both sides by 1.85. All right, let's go back to the calculator because that's not math I want to do in my head. 3.58974 divided by 1.85185. Okay, 1.938 is pretty close to 2. 1.93846. All right, and that is equal to 0.072 divided by 0.036. You should recognize those numbers without having to use your calculator. 72 is twice the size of 36. Yeah, 36 times 2, so 0.072 divided by 0.036 is just 2. And it's raised to the y power. So even though this doesn't work out exactly perfect, we could say that this is like having 2 equals 2 to the y power. Therefore, the value of y is 1. So this reaction is first order with respect to the iodide as well as the thiosulfate. So what we can do now is write the rate law. And here's how we summarize it. The rate is equal to K times the concentration of thiosulfate to the first power, which I'm not going to write the 1 in, we don't need to, times iodide, also to the first power. So overall, it's a second order reaction because it's first order with respect to each of our substances. All right, so we've answered part A. We have written the rate law. Now we have to answer part B. Let me remind you what the question was asking. Part B says determine the value of K with units. So now is where we would take one of our experiments. It doesn't really matter which one. Let's just pick one. How about the first one? Sound good? And we're going to put in those numbers. So for the rate, that was experimentally determined to be 2.6 times 10 to the minus 6 moles per liter per second. And then the concentration of thiosulfate in that experiment is 0.018 molar. And that's raised to the first power. And the concentration of iodide is 0.036 molar, which is also raised to the first power. So to solve for K, I simply need to take the rate divided by concentration of thiosulfate and concentration of iodide. Now let's look at the units and see what the units are going to do before I mess with the numbers. I can cancel out one of my big M's, but the other M has to stay there. So my units are going to be 1 over molarity times 1 over second. Now let's do the math. Get your handy calculator out. Okay. So 2.6 times 10 to the negative 6 divided by the product of 0.018 times 0.036. And I get 0.004012. So the value of K, how many sig figs do we get to keep here? It looks like only 2, so we'll round this number to 2 sig figs. And its units are per molar and per second. So now we've answered part A and we've dealt with part B. Let's address part C. Part C is asking, how is the rate of disappearance of thiosulfate related to the rate of disappearance of iodide? Well, in this case, we simply have to look to stoichiometry. Whoops. So for part C, we can say that for every 1 mole of thiosulfate that is consumed, three moles of iodide will be used. That means that the rate of disappearance of iodide is 3 times the rate of the disappearance of thiosulfate. Remember the graphs we saw in the last podcast? This is where that all came from. As the concentration of thiosulfate goes down, the concentration of iodide goes down 3 times as fast. Last question, part D. Part D says, what is the rate of disappearance of iodide when thiosulfate concentration is 0.015 molar and iodide concentration is 0.040 molar? So we don't have that information in our data table, but we do have a rate law that allows us to calculate exactly what it's going to be. So let me get back to my white screen and we'll do this math. So we just take our rate law where we said that the rate is going to be K with a value of 0.015 0.04 per molar per second times the concentration of thiosulfate, we were given 0.015 molar, and the concentration of the iodide. And since they're both raised to the first power, we don't have to do any mathematics. It's just canceling out our units and then multiplying. So let's get our calculator and do the multiplication. 0.04, oops, not enough zeros. 0.004 times 0.015 molar and 0.04 molar. So at that concentration, I get a rate that's not the same as the one I got before, but it's just a rounding thing. So the rate is going to be equal to 2 times 10 to the minus 6 moles per second. So when we have exactly those concentrations, we can find an instantaneous rate, not the average rate, but an instantaneous rate at that particular moment of the reaction. There you go. That's how we work with the differentiated rate law. In the next part of the 12.2 podcast, we'll investigate how to apply an integrated rate law instead.